Okay, we're going to start with chapter 11 today. We should finish the whole thing. So I hope you got the email that the exam was curved by 8 points. I think not a lot to say. It was kind of rough. If we finish 11 early enough today, I'm happy to go through some of the questions. Otherwise, I'm pretty sure we're going to have a full day on Thursday of review, because I don't know if chapter 12 will take that long either. It's going to depend a lot on how, I guess, the recovery from the alkene chapter goes. So we're going to go ahead and get started, unless there are any questions beforehand. Okay, let me switch this over. Okay, let me pull up last year's stuff. Okay, so chapter 11 is radical reactions. And in radical reactions, what we are going to be focusing on are reactions that utilize homolytic bond breakage or cleavage. These are the same words. So homolytic bond breakage and bond formation. What that means when you talk about homolytic bond breakage, it means that you're going to have symmetric cleavage. So you're going to move or going to show movement of one electron at a time, or movement of single electrons. So if we draw a system that's undergoing this homolytic bond breakage and cleavage from your compound, homolytic means the same. So the same thing has to happen for X as it does for Y, which means one electron in the arrow goes to X and the other electron in the bond, goes to Y. So you're going to use these single barbed arrows. And the product of that are going to be radicals. So the radical systems have odd numbers of electrons. Okay, or they have, they'll have one electron that's on its own. Okay. Now to show that the bonds reform, this is kind of the only time you're allowed to draw electrons as if they're just going into space. So you just reform the bond, showing one electron comes in from X, one electron comes in from Y, and that's a 2-electron system which will reform that sigma bond. Okay, so on this side we break, and this side it's shown that we're making these. Hold on a second. That was weird. Mine of a ghost. Okay, so when we talk about the radical, we're going to have our carbon in a situation like this, where we have p orbital that is going to hold that electron. Okay, so that's one way to visualize the electron. The other way, or the carbon system, or you can show it, and this is kind of hard to draw, where instead of it being a p orbital, that electron is in an sp3 orbital, and this is sort of like a shallow pyramid. They're very hard to study because they're highly reactive. This would be trigonal planar. And if it is more like a shallow pyramid, this will invert rapidly. But for the most part, they're fairly much planar. And the structure is going to be like halfway between a carbocation, which would be a carbon with a positive charge, 3 bonds, and a carbanion, which would have 3 bonds and 1 lone pair. So both of these are sort of adequate representations of the radicals. At this point now, we're going to look at what will be on these ends and how that affects the stability of the radical. In this case, what you're going to need to do is focus on the number of R groups, just as you did for the carbocation stability, and actually they mirror one another. So if you have what we would call a methyl radical, it has 3 hydrogens, and then a primary radical would have 1 R group. Oops, that's supposed to be an electron. Secondary would have 2. And the tertiary would have 3. They could be the same or they could be different. And just like with carbocations, the stability increases from left to right. Now, the theory behind this is in molecular orbital theory with, again, this idea of hyperconjugation. But the best way to consider this for both the radical and for the carbocation is that you could just say carbon misery loves company. Okay, so the more R groups you have to support this carbon with the radical, the more stable the system would be. All right. Other thing we have to consider for radicals that's similar to that with the carbocations is that radicals can be resonance stabilized. So, for example, instead of having an allylic carbocation or an allylic lone pair, you can have an allylic radical. And in this case, what you would show is a 3-arrow proposed structure or arrow diagram if they move, but again, of course they don't, and you would end up with the resonance structure. Okay, now just like you did in chapter 2 with resonance and MO theory, you can do the same MO theory analysis here. So when you do your resonance structures, you're going to use 3 carbons, which means you're going to need 3 of the p orbitals, and you're going to make 3 molecular orbitals. So on your energy level diagram, you would have bonding, non-bonding, and anti-bonding. And then what you would recognize in your resonance structures is that there are 2 electrons in the pi bond and 1 in the radical. So that's a total of 3 electrons being stabilized. 2 would go into the lowest energy molecular orbital, and 1 would go into that non-bonding middle energy orbital. Okay. So the other system that also has the stability in terms of placement, you can get stability on a radical that is benzylic, and that would be stabilized throughout the ring. But what I want you to also recognize is you don't ever have a vinylic radical. So you can have it benzylic, allylic, but not vinyl. So these vinylic radicals do not happen or are unstable. Okay. Are there any questions so far about radicals, the ranking of stability, or going back to that idea of the molecular orbital diagrams?
I have a quick question.
Sure.
Is it always true that as stability increases, then it's inversely proportional to reactivity?
Let me draw something real quick. I guess the best answer is yes and no. Because let's say we have our energy level diagram here. And we're going from reactants to something. Okay. And just for the sake of argument, we'll use the tertiary, the radicals and stuff. So the tertiary radical, these are reactants. And is more stable than a secondary radical, which is more stable than a primary, which is more stable than a methyl. Okay. That's the lone electron. Okay. Now, if you ignore this part, the reaction or the reactants, and you just say, this is the relative energy level diagram for these species, okay, then you would say this would be the most unstable. So it would be the most reactive. And this would be the least unstable. So it would be the least reactive. But essentially when you incorporate this part, what you see is that these have too high of an activation energy to even ever be formed. So the activation energy to come up to a methyl radical might look like that. And the height of the hill is massive. So methyl and primary radicals aren't going to form. So saying that they're the most reactive radical is true. However, it's hard to make them, so they're essentially then not participating in reactions anyway. Whereas secondary and tertiary radicals, these are going to have lower activation energies, which is going to make them easier to form. But radicals as a family are considered high reactivity species because electrons like to have a partner. So like, if you follow like any kind of like, I don't know, like cosmetology or anything with like these, when they promote like skin care for people that are my age, they talk a lot about like, oh, you have to neutralize your reactive oxidants and your reactive species because it causes damage to your skin and your brain function and all that stuff. And it's because these radicals that form are going to need an electron because they're so reactive anyway. They're going to just take an electron from anything it can find. And biologically speaking, that causes aging and issues. But to say that, like, yes, this is the most reactive, but you would have a hard time making it. Does that make sense, Karen?
Yeah, that really helps me understand the order of
And
things.
the same thing would be true with carbocations. Like a methyl carbocation would be the most reactive carbocation. However, the activation energy is so high, you're going to have a hard time making it. And so, so it ends up being almost like a moot point, like, because you can't make it. So its reactivity kind of doesn't matter. But everything's a probability. And so when you look at if you look at a energy diagram, like where you have energy and you have the number of molecules, and this would be in your sample, and this would be at some temperature. You have a distribution, which is like, it looks like it's a Maxwell-Boltzmann distribution. So most of the molecules have this energy associated with them. If the activation energy of the reaction is up here, then only these molecules that have high enough energy are at this point, maybe, wait, no, I have these axes wrong. This is number of molecules. And this is energy. So only the molecules that have energy greater than the activation energy would participate in the reaction. If you warm this temperature up, then you would shift the distribution and you'd end up with more molecules with more energy. So saying that this doesn't occur, it's just so improbable. And the same thing would be true of the methyl carbocation. Any other questions about this sort of thing? Okay, so one of the things that we've said sort of from the beginning is that alkanes have very low reactivity in the sense that they make really good solvents and you can burn them. But one of the things that alkanes will do is alkanes will participate in radical reactions when in the presence of X2 and this is h nu, so Planck's constant times the frequency, and that just means light. So in the presence of light, alkanes will participate in radical reactions. And we're going to use an alkane reaction, but what we have to do is we have to look at radical reactions as a whole. So the reaction that we're going to look at is what would happen if we would take methane and react it with chlorine. So this would be a gas phase reaction. And then we're going to shine some light on it. And this wavelength of light would depend on which halogen you were using. So the specific wavelength doesn't matter, but a wavelength required to homolytically cleave the chlorine into radicals is a different wavelength than that would be required for the bromine. But regardless, when you do this reaction, you're going to make chloromethane and release hydrochloric acid. Okay. And then what I want you to write at the end of this is plus other stuff, because what we're going to find is that radical reactions are very hard to control, and you end up making a significant amount of byproducts. All radical reactions, or their reaction steps, fall into one category. I guess one of three, but you can categorize them. The first category, and this is going to almost essentially always have to happen first, is you have to have an initiation step. Okay. And the initiation step is in the step in which you create a radical. Okay, so your radical is going to be a product. Okay. The second step is called a propagation, or the second type of step is a propagation. Okay. And in a propagation step, you move the radical from species A to species B. Okay, so it just moves around to different components in your reaction. You have radicals as reactants, and you have radicals as products. The third step is called termination. And in termination steps, you essentially kill the radical. You put two radicals in as reactants, and then you form a stable compound or a stable product. Okay, my cat's crying. Hold on a minute. So one thing that you'll have to be able to do is, if you see a step in a radical reaction, identify it as initiation, propagation, or termination. So what we're going to do is we're going to look at this reaction from the perspective of these three steps. So in this reaction where we have the formation of the chloromethane, the first step, which is initiation, which is always formation of radicals. The initial formation of the radical involves only the chlorine. Oh my goodness, I'm running out of pens. This one's good. So you have your chlorine. Oh, let me draw it as a diatomic. And in the presence of light, and again, it would have to be a specific wavelength, this sigma bond between the two chlorines is going to homolytically cleave. So one electron goes to the chlorine on the left, one goes to the chlorine on the right. And then you make the neutral chlorine radicals. Okay. If this was a bromine, you would have obviously diatomic bromine, a wavelength of light, formation of two bromine radicals. Now in propagation, we just have to move the radical. Okay. When you consider these propagation steps, there's lots of them. This is where you lose control of your reaction. So, for example, you could have methane, and it sees a chlorine radical. Okay. This bond will homolytically cleave. Actually, let me take that. Homolytically cleave. And you're going to end up with a methyl radical and HCl. Okay. So you've moved the radical from the chlorine to the methane. So you have a methyl radical here. Okay. Now what this radical does next is unpredictable. Okay. So this radical, if you're lucky, just finds the second chlorine radical and you make a product. Right. But this radical could find a diatomic chlorine and make a chlorine radical. So there's tons of these reactions, and the more you do, the more times you let the reaction occur, the different, you're going to get a generation of different types of radicals. Okay, and this actually, I lied here. This is a termination step. Okay, so let's say you have your methyl radical, yeah, and then it finds a chlorine. Sorry, I messed up. You make product, and you release a chlorine radical. Okay, let me move this back up so I can draw a few more propagation steps. Oops, I should give you more time. I'll erase first. All right, so let's say we have something else happening, and we have this radical formed a lot. And what happens if this radical bumps into one of these molecules that you've already made? Okay. Okay, my cat's coming to visit you guys today. Then you would reform methane, and now you would have this radical. But if this radical finds a chlorine, then you're going to make dichloromethane. So this is where you see with these propagation steps where you lose the control of the reaction, and you can end up generating radicals in the solution that are going to lead to products that you're not particularly interested in. At some point, then, you have to have a termination step. And in the termination, you have to kill the radical. And it would be any two radical species meeting together. So you could have the one I drew on accident the last time. That would kill the radical. But you could also have this methyl radical meet another methyl radical. And you would end up making ethane. So when you perform these or have these radical reactions taking place, you definitely will make your intended product. But you're going to get lots of side products. So at the end of this, we'll look at ways in which we can control to some extent the types of radicals, but this is a good, easy reaction to write where we can show all the steps. So if you see a radical step, and you need to be able to classify it. This is a termination step, this is propagation, etc. Are there any questions about that? The types of steps involved? Okay, so we're going to jump ahead to section 11.7, which is called allylic bromination. Okay, and the name of this reaction tells you exactly what's going to happen. You're going to put a bromine in an allylic position, but in order to be allylic positions are relative to vinylic position. And what that tells you then is that you're going to put a bromine on an allylic carbon, which is one carbon away from an alkene pi bond. So before we go into the allylic bromination reaction, we have to consider why the bromination reaction always ends up at the allylic position. Okay. So what we're going to do is we're going to just start with cyclohexene, and we're going to look at the three different hydrogens that are present in this compound. There's three more on the bottom, but the three on the top are exactly the same as the three on the bottom. Okay. We have three positions. This one is the vinylic. Okay. This one is the allylic. This one is the alkyl. So if we look at the question, how do we know, or what is the evidence for that bromination will occur at an allylic position? Okay. And the way we're going to do that is we're going to look at the bond strength. So we can have a vinylic carbon to hydrogen bond, an allylic carbon to hydrogen bond, and an alkyl carbon to hydrogen bond. And look at the relative strengths, or the bond energies of these bonds. Vinylic carbon to hydrogen bond. So this bond right here is 444 kilojoules per mole. Okay, so it's going to require 444 kilojoules to break that bond. Okay. The allylic, 364 kilojoules per mole. So significant, about 100 kilojoules per mole, 80 kilojoules per mole less. The alkyl is 402 kilojoules per mole, which means the allylic carbon to hydrogen bond is the easiest bond to break. Okay. It's the easiest of the three bonds to break due to the fact that the resulting radical is resonance stabilized. I'll buy some more markers today. These are too fat. Okay, so if you make an allylic radical, then you can stabilize it through resonance. If you can stabilize something through resonance, it means the original process is easy to do. Are there questions so far before we look at the reactions, the potential reactions that are involved in allylic bromination? Okay. So since that allylic site is the easiest site to break, we could do the reaction that we just looked at, where we take some bromine, we have a compound, we put in some light, and we're going to end up with bromine up here. And this would be through the same mechanism as you saw for the methane plus the chlorine in the presence of light. It's still going to go to this bromine or this allylic position because that's the easiest bond to break. Okay, but what I didn't tell you is that when you use the light, you use the light as a laser burst, which means you don't continually have a light source on. Okay, so the light is on only momentarily. Okay. So this is one reaction that will take place when the light is on. So light on. Okay. But when you turn the light off, okay, so this is just a burst, then it turns off. Then you end up with reaction conditions that look like this. Okay, this is a halogenation reaction from chapter 9. That's going to go through that bromonium ion intermediate, and you're going to end up with a mixture of enantiomers. So when you do the original reaction we just discussed, you're going to end up with a minimum of 3 products. Okay. The limitation in the X2 plus light is you cannot stop the halogenation side reaction. So these end up becoming competing reactions. So the conditions of the allylic bromination stop the second competing reaction, this halogenation reaction, from occurring. So what we're going to look at is a specific allylic bromination step that prevents side reactions. Okay. Are there any questions about why these two would compete in this experimental setup? Okay. So in allylic bromination, where we prevent our side reactions, we're going to have our initiation step use a compound called NBS, which stands for N-bromosuccinimide. Now, the entirety of this reaction you don't need to know, because the reaction that the NBS undergoes during the course of allylic bromination is a sort of a cyclic process where it kind of feeds back on itself. So you end up having like 2 mechanisms occurring at the same time. So we're not going to focus on that, but we will look at the initiation step. So you need to have this 5-membered ring. A couple carbonyls are on here. And then you have your nitrogen bonded to a bromine. Okay. Okay. This you will shine light on momentarily. And then what you make are these 2 radicals. Okay. This bond is easily cleaved, or homolytically. And these products go on to do 2 things. Okay, so this one is going to perform a reaction with your alkene substrate. And this part is going to end up getting recycled. Okay. And the recycle process is going to keep the concentration of bromine and HBr low. So what that does is it's going to prevent 2 kinds of reactions, the halogenation reaction and a hydrohalogenation reaction. Okay. And so what you end up doing, and you'll see where the HBr comes in a minute, it ends up allowing you just to have your allylic bromination product. So are there questions about these products and what we're going to do with them? Okay, so I'm just going to take this bit off so I have more room to write the next step. So we have our initiation step. We formed our bromine radical. Propagation initially has to be, I'm going to draw this hexane on its side so that the allylic position is out like this. Our initial propagation step, we have to have a radical come in and we have to move the radical to a different position. So the first step in the propagation is going to be this hydrogen radical abstraction and the formation of the resonance stabilized allylic radical. And you're going to make HBr, which if you didn't have a feedback loop to keep this concentration low, this would cause hydrohalogenation on any of the reactant alkenes that hadn't participated in this step. So this ends up going into a feedback loop to keep concentration, and concentration is square brackets, low. So then the termination step that's important is when the allylic radical finds another bromine radical. And then you make your product like that. Are there questions about this allylic bromination before we consider product mixtures? This is a symmetric system, so you have two allylic positions here, and they would both look like this.
I'm a little confused on when do you go from the 5-member ring to the 6-member ring?
Oh, this is a reactant. So this is the alkene. So remember, we're doing allylic bromination, so we have to have a substrate that has a hydrogen in an allylic position, so you have to have a pi bond in your reactant. So this is not this. These are two totally different things.
Okay, I just wanted to make sure. Thank you.
Yeah, so the way this reaction would be written out on your arrow would be that you would have your reactant alkene like this. And then what you would see over the arrow is the NBS and light. This is the condition. That's all you need to see in order to get allylic bromination, and then your product would just be this. So you wouldn't even necessarily have to draw the NBS, but if you see it, you need to know what the structure looks like so you can associate the letters or the abbreviation with an actual compound. Now, depending on the position of your alkene in your substrate, it's not uncommon in allylic bromination to get a mixture of products. But they're all allylic bromination products. It's not, you don't have hydrohalogenation and you don't have halogenation happening. So for example, if we take this substrate, which has an alkene, so this is the allylic carbon. And if you put this into a condition of NBS with light, then the first thing you're going to make is this allylic radical. Okay. This can then be brominated in that position. But this allylic radical is also resonance stabilized. So the radical reactivity sites are this tertiary carbon, but also the primary carbon. So you're going, oops, gotta have my pi line. You're going to end up with a mixture of products, and it's unavoidable due to resonance stability. So once you make that initial radical, if the compound is asymmetric, then you're going to get a mixture of products because of the resonance stability. You can't, this is just, remember, these are just like the extremes. You can't, this isn't the same thing as saying like you're gonna have a carbocation rearrangement. This is saying that these two things simultaneously contribute to what the actual structure is that's participating in the second step, which is adding in this termination step to get to the bromine on the system. So these would, you would end up with both of those products. Are there questions about allylic bromination? Okay. Now we are going to, we're making really good time. Okay. The next thing we're going to do is go to 11.11. And this is called radical polymerization. And we'll look at a few examples. I'll have to pull the slides up to show you a table. But just to start, we're going to kind of talk about the polymerization reactions from the perspective of the wording that you use to describe things. So you have your reactant, and the reactant, oh my gosh, is an alkene. Okay, an alkene reactant, which may or may not be substituted. It depends, you know, this is just a plain example where we have ethylene. And we're going to have the ethylene undergo polymerization. So how you draw the product then is you're going to draw a square bracket, and then you're going to draw your carbons staggered. And these two carbons are these two carbons. And they end up as sp3 carbons. And then outside the square brackets, you see a little number n. Okay. So this part of it, the reactant, is called the monomer. Okay. The polymer is a repeating chain of monomers whose pi electrons were used as links or linkages. So there would be another 2-carbon group over here and another 2-carbon group over here. Those bonds from an original carbon to a new carbon from a new molecule, those came up. You are going to use the pi electrons. These are going to be used. Okay, so when you have your polymer isn't going to have, it's going to lose the pi bond between those carbons. Okay, but when you name this, you're going to call it poly because it means many, and then you use the actual name of the monomer, polyethylene. Okay, so even though there isn't an ethylene molecule in the polymer anymore, because you don't have the pi bond, you just say you have many ethylenes that were linked together to make a polymer. Okay. And here, N is the number of monomer units. And to be honest, I don't really know how, in an industrial sense, you control the number of monomers you have in there. That would have to be a later, more advanced class on, excuse me, polymer synthesis. But these reactions still follow those same 3 steps. Okay, so you are going to have an initiation step, but your initiation step is going to involve a peroxide being subjected to heat. So that little triangle stands for heat. And you're going to make 2, RO radicals. Your propagation steps are going to be used to build up that N number. And then at some point, you'll terminate and kill the radical. So I'm going to try to find my slide that has the table that I need you to look at in the notes. Okay, here it is. Okay. So this is a table from your textbook. And what it's showing you is the structure of the monomer and then the resulting polymer. So this is the one we just sort of looked at on the whiteboard where we had ethylene and then we make polyethylene. And it's just showing you how these things end up being drawn inside that square bracket that would be repeated some number of times. And then just for your knowledge, you are very exposed to polymers. So polyethylene is used in bottles, plastic bottles, manufacturing materials in terms of packaging, Tupperware. Here's another one, propylene. So you make polypropylene. It has a methyl group on it. It's for carpet, car tires. Now styrene, this pH up here, that's a phenyl ring. So you end up making polystyrene that has an aromatic ring, that's styrofoam. Vinyl chloride, so PVC piping, polyvinyl chloride for plumbing, things like that. And then this is tetrafluoroethylene, and you make polytetrafluoroethylene, which is Teflon. So this is the compound that's on your nonstick frying pan. So what is going to be important is if you see the polymers drawn in this way, square brackets with an N, square brackets with an N, square brackets with an N, that you can take that polymer and work backwards to figure out what monomer had to have been used to make the polymer that's shown. Right. Okay, Are there questions? I will go through the reactions because, or sort of the formation of a small polyethylene, just because the reactions tend to get a little messy, and then the way they're drawn looks a little funny. But are there any questions so far about this type of table or what you need to know from it, or anything that we've talked about polymerization up to this point? Okay, so let me erase. And so what we're going to do is we're going to show formation of polyethylene. Now this isn't going to be like a useful polyethylene because R is going to, or N is going to end up very small, but it'll at least show you the 3 steps. So the initiation, again, is where you take your peroxide and you heat it. And you make these 2 radicals, they're identical, and they're called alkoxyls. Alkoxyl radicals. Okay. Then you're going to have a series of propagation steps. So we have to move the radical around. Okay. So what we're going to do is we're going to draw our ethylene monomer with our alkoxyl radical. Okay. We're going to form a bond and generate a new radical. So this part here is the sigma bond that's left over from the ethylene. The radical's on that far carbon, and we have a new bond formed here between carbon and the alkoxyl radical. Okay. Now this species has to react with a second ethylene. So we have another ethylene here. And a radical. And now when we link these 2 species, we're making a new carbon-carbon bond. So we have 1, 2, 3, 4 carbons involved. 1, 2, 3, 4 carbons involved. So this is the original piece. This is the new carbon-carbon bond, and there is your radical. Okay. And then this radical could meet another alkene. And make another new carbon-carbon bond. Okay, now again, 2 carbons, 4, 6. 2, 4, 6. Radical. Okay, so we've used 3 ethylenes so far to make this polyethylene. Then in our termination step, what we'll show is 2, 4, 6, finding 2, 4, 6. Okay, so we have 1, 2, 3, 4, 5, 6 ethylenes being used. So what we would write is RO up into our square bracket, carbon, carbon, up, OR, 6 times. And that would be the formation of, in this case, a small polymer. Are there questions about any of those steps in this reaction? Okay. All right. So the last part of this chapter is 11.13. Wait, yeah, that's right, 11.13. And it is the halogenation, radical halogenation as a synthetic technique. And we're going to look at 2 different types of radical halogenations. Okay. The first type is radical chlorination. And radical chlorination is useful when your alkane substrate has only one kind of hydrogen. Okay. So what I mean by that is, let's say you have cyclohexane as your substrate. Okay. All the hydrogens are on sp3 carbons, and they're all essentially identical. You have axial and equatorial positions, of course, but this compound is conformationally mobile, which means it undergoes those ring flips. So the hydrogens are all equivalent. Half the time they're equatorial, half the time they're axial. But in the presence of chlorine with light, you can get this chlorocyclohexane product. Okay, this is a very fast reaction to perform, and the reason it's only used when you have a single kind of hydrogen is because the chlorine radical is not very selective. Okay, the chlorine radical is not selective about the type of hydrogen it takes. Okay, or replaces. So when you perform this reaction, as long as they're all the same, chlorine is fine. Okay. But if you have different types of hydrogens, you're going to use radical bromination. And the advantage to using the radical bromination is that it's a slower reaction, but the bromine is more selective about where it's going to end up on your compound, and you end up avoiding mixtures. So for example, if we look at this substrate, we have lots of different types of carbons and therefore lots of different types of hydrogens. So we have primary here, secondary here, primary, primary, secondary, tertiary. So since the bromine is more selective, when you perform this reaction, you're going to avoid a product mixture and always put the bromine on the more substituted carbon in your alkane reaction. Now, if this compound, the limitation, of course, of this compound is it could create a chiral center. Depends on the structure of your substrate. But it could end up making a chiral substrate here, or a chiral product. So that's just something to consider, because then you would end up with a mixture of enantiomers here, and you may not want a mixture of enantiomers, but it may be unavoidable. Okay, so why this is important is that we went from having this pretty boring alkane that we can't do much except solvent and burn, and then we made an alkyl halide. So what we did essentially in going in this direction is we did a functional group transformation. Okay, and you have a lot of reactions that you can perform from alkyl halides. Okay. So once you have your halogen in there, all of the other reactions that you've learned are on the table. So for example, if we take this compound and instead of doing bromine and light, which you can do, you could also do the NBS and light. That will still make a bromine radical. Bromine radicals are still selective in this condition as well. So you're going to end up with your bromine in that tertiary position on the ring. Okay. Substitution is possible. Now in this case it's tertiary, so it would have to be an SN1 reaction. But you could do a substitution on here and make an ether, make an ester, all sorts of things you know how to make now. Or you could do an elimination, make an alkene, and then from your alkene, you have all your chapter 9 addition reactions. So this step here of making this functional group transformation to end up with an alkyl halide brings you into a synthetic situation where you can do everything that you've learned this entire summer term. So that is, we made great time. That is the end of chapter 11. Are there, okay, let me see what this question is. It's magic, you're right, it is. And let me tell you, some people who have a good control, I mean, you can make a lot of money as a synthetic organic chemist. But, okay, it is magic. So are there any questions about chapter 11? Okay, so I don't want to start chapter 12 today because it's really a nice review chapter for all of the reactions. So I'm going to wait to do that until tomorrow. So if you'd like, I'm happy to answer any questions about the exam that you might have. Let me pull up. Oh, it's harder to do it this way. Let me pull up the exam, see if I can do it. see. Let's see. Okay. Okay. All right. So I think I can do it this way. So this is, it's going to be kind of hard to see, but this question is which arrow is drawn incorrectly. And when you look at your arrows, remember you always have to have the tail on electrons. So the incorrect arrow is B because it's going from the positive to the electrons instead of the other way around. Okay, so number 2, this question is, it's giving you a reaction, but the analysis is with regard to the stereochemistry. So in this case, let me see, annotate. This reaction is using a secondary substrate, a strong nucleophile, and a polar aprotic solvent, which means this reaction is SN2. Okay. If you do the analysis, so SN2 reactions, these are going to invert the stereochemistry. So this first, well, and everybody's answers get a little bit scrambled. So you have to know whether this is RS and then the product will be the opposite. So let's see, the bromine is going to be 1, the ring 2, the methyl is 3, and then the hydrogen that's not drawn is 4, but it's in the wrong position. It's coming at you instead of away from you. So this looks like it's S, but because of that hydrogen in the wrong spot, it's R. So with complete inversion, the only product will be S. Are there any questions about that, about number 2?
I felt a little confused only because it says the only product form will be the S enantiomer, but it doesn't say, like, I don't know, the way it was worded, it's just like enantiomer of what?
This. So well, you're going to make
it places the BR.
Right, you are going to make a new compound.
Yeah, so that, I got it right. It just was like really anxious about picking that one because.
Okay, I understand what you mean, because what you do make is the hydrogen will be pushed to the dash and the cyanide group will end up on a wedge. But since that compound is chiral, it will have an enantiomer. So the two product choices that you have for SN1 and SN2, since it's secondary, it will end up chiral. And it's just, of those two products, do you make the S enantiomer, do you make the R enantiomer, or would you make the mixture of the enantiomers? But you always invert from your reactant in SN2. But I see what you're saying. It does seem a little, the terminology, I think, I don't think it's misleading, but I don't think it's not maybe crystal clear. Other comments on this one? Okay. Nucleophile, best nucleophile is going to be sulfur species that are negative. The oxygen species are better bases. And if you have to pick between neutral and negative, you always pick your negative will be the best nucleophile. Okay. This is the rate law. So this is, which you need to recognize that this is a, you're shown it's a substitution. So even though this is a weak nucleophile, and this is a tertiary substrate. So it's going to go in a two-step reaction by forming the carbocation. So it's an SN1 reaction, and only the substrate will be found in the rate law. So it would be the rate equals K 2-iodo-2-methylbutane. Okay, so this one, what you have to do, and if anybody wants me to draw this out, I'm happy to, but you have to draw your substrate and then figure out what you would need for SN1. Because I think what you, typically for SN1, it favors weak nucleophiles and polar protic solvents. But I would always double check to make sure that the substrate works itself out. But weak nucleophiles and polar protic solvent is the best conditions for SN1. Okay, so the mass spec is of an alkyl halide, and then you undergoing a nucleophilic, or sorry, substitution. This is the mass spec of the product. You have M and M+2 shown with masses as a 1-to-1 rate, almost a 1-to-1 ratio, which indicates bromine would be used as your nucleophile. Polar protic, so you need to have a hydrogen in a polar bond. So it would be this ethanol. This is DMSO, the hydrogens are in nonpolar bonds. This is diethyl ether, same, where you have hydrogens in nonpolar bonds. And this is dimethyl DMF. Dimethylformamide is this one. But again, you have hydrogen to carbon, nonpolar, CH3 groups here, nonpolar. Oh, sorry, not nonpolar, aprotic, because the hydrogens are in nonpolar bonds. Okay, the E stereochemistry, this one would be tossed out because you can't rank those two. And so this one would be high, that one is Z. High, this one is Z. Wait. Fluorine, bromine, fluorine, chlorine, bromine. High. So that is Z. This one doesn't count. High. It's this one right here. The bromine and the iodine here. Nomenclature of the cyclohexene. Questions? So you would have to pick the most substituted alkene. So this one is trans and disubstituted. This one looks disubstituted, but it's really only monosubstituted because the pi bond here, it has to be in the parent. Cis alkene, this is trisubstituted, so it would be this one down here. Most reactive in SN2, you need backside attacks, you need methyl or primary. This is primary, secondary allylic, vinylic. So this one wouldn't work at all. So this one up here is the correct answer. Okay, so in this one, you have to talk about the functionality of the pi bond, right? So these are pi bonds, but they're in rings, so they're in conjugated systems. So the alkene is right here, and it's trans and di-substituted. Okay. All right, so this is the ozonolysis, which means you have to break off, break at the alkene points. So you'd have to break it here and break it here. So you would do a ring opening here, and then you would release formaldehyde down here. So you are actually going to have two products for this reaction. And it would be, this is the answer, because it opens the ring, generates a bunch of ketones, or well, two ketones and an aldehyde, and then releases formaldehyde.
Dr. Walters, I had a question on the last one.
Okay, not this one, but before?
Yeah, the one previous, this one.
Okay.
When I looked at this one, I saw that the two alcohols were actually cis, and it kind of contradicted the trans as well, because
But these aren't necessarily cis, because you get free rotation around all these things. Cis and trans doesn't apply to single bond networks.
Okay.
Because all of those sigma bonds will rotate. So it's just in drawing this part as, sorry, let me get in the spotlight. Drawing this part out here as a chain, they both end up on dashes. But if you rotate around this pi sigma bond right here, this hydroxide would end up on a dash.
Okay, that makes sense.
Okay. Okay, so this is your substrate alkene. The acid here, this means acid catalyzed hydration. That means you're going to make a Markovnikov alcohol, and you see the alcohol stretch right here. So when you look at your options, you have to be sure that you have your alcohol on the more highly substituted carbon. And that would be this mixture. The problem the limitation to acid catalyzed hydration is you go through a carbocation. So attack can be at the top and the bottom, which is why you have to show the enantiomers here. Okay, so this question, these set of conditions, this is hydrohalogenation with anti-Markovnikov addition. So your bromine is going to end up out here on the outside of this methylene group. The bromine's supported by the the mass spec. This one right here. Oh wait, sorry. I keep forgetting that you can't see my mouse, this one. Okay. So this is hydroboration oxidation. So this is anti-Markovnikov addition of water. And they add with syn addition. They add both on the bottom side of one face. Okay, so you're told you're doing an E1. E1 reactions or E1 eliminations tend to make the Zaitsev product. E1 is two-step. So you would make a carbocation intermediate. it should be a Markovnikov. Yeah, it should be this one. This is what I would have picked. Yeah, so E1 eliminations make the ZEF product in a two-step reaction going through a carbocation intermediate. So that one here. Oh, okay, so this is hydrogenation. You can't do anything on the ester. So the only thing that the ester is this part over here. The only thing that you can add hydrogen to is this set of pi bonds throughout this long chain. So it would be this last answer here. Okay, which of the products shown are enantiomers formed as products upon reaction of HBr with 4-methyl-1-pentene? Okay, this one I'm going to have to draw out. So pentene has 5 carbons. Oops, that's 6. 1 pentyne. 1, 2, 3, 4. Okay, HBr. And enantiomers. Okay. Okay, so okay, so this is your secondary carbocation. This carbon is secondary, this is primary. So this carbocation is not going to rearrange. So when you have the attack, it'll occur on the top and the bottom. So you're going to end up with bromine here on a wedge and on a dash. Okay, so B and D. Okay, vinyl cyclohexene in bromine and water. So this is halohydrin formation. So you're going to get a bromine and an alcohol and an OH group after a deprotonation. The hydroxide is going to end up on the secondary carbon and the bromine on the outside. So it would be this one. And I'm happy to draw the mechanisms of these if you want to. If you want me to, you just have to say. Okay, so this is halogenation. Adding 2 bromines, one on the top face, one on the bottom face. They add with anti-addition. So the bromines in the product have to be 1-1 wedge, which is right here. Okay, so in this question, it's a 2-step reaction, MCPBA as well as the acid. So these conditions take you all the way to a transdiol. So you would want the OH groups shown, one on a wedge, one on a dash, and then you would end up with the enantiomer. Okay, so the intermediate for oxymercuration, that's called the mercurinium ion. should be this. But the mercury should have a formal charge of plus. I'm going to talk to Dr. Barrios Sosa about that one. Because the mercury is making 2 bonds here. And it would have a formal charge of positive. I'll check on that one, number 23. Okay, all right, so in this question, going from an alkene to an alcohol, so that's hydration. And you're adding to the less highly substituted carbon, so it's anti-Markovnikov addition of water, so that is the BH3 and THF reaction conditions. Okay, so in this case, you are taking your alkene and you're making a cis diol. You need osmium tetroxide for that. So it would be this last answer. Okay. Are there any questions that anybody has about anything else on the exam? Excuse me, or anything from today? All right, well, we will wrap it up the next couple days with chapter 12, and I will talk to y'all soon. Have a good rest of your day. Bye.
Thank you.
Yep, you're welcome.